Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. For tonight, we're going to make sense of functions with the TI-Innovator Hub and the TI-84 plus CE graphing calculator. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough to teach, tough to learn concepts accessible to all my students. I'm excited to be joined by our panelists tonight, Dennis Wilson. For the last 24 years, Dennis has been teaching at Landmark Christian School in Fairborn, Georgia. He has taught every level of math offered at the Landmark from 5th grade all the way up to multivariable calculus 2. In 2012, Dennis presents annually at multiple conferences on technology on how he uses math in the classroom. He has served as an AP reader for calculus for the past 5 years and formerly served as the president of the Georgia Association of AP Math Teachers. Dennis, it's great to have you with us tonight.
Thanks, Mike. It's great to be here.
We're expecting a large crowd, so your audio is muted. Feel free to send questions to Dennis using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the certificate of attendance as well as a link for the documents at the conclusion of the webinar. We hope you don't have any audio issues tonight, but in the event that you do, try toggling the audio broadcast button at the bottom of your WebEx screen. At this point, Dennis is going to discuss our agenda.
Thanks, Mike. So tonight, we just did our welcome and introductions. And what we'll be looking at tonight is the language of functions. How do students discuss it? What do they say? What do we want them to say? We'll look at simulating functions using programs on the TI-84 CE. We're going to be looking at using the TI Innovator Hub to take in input, but also to give us output. And even though it's at the end of this list, extending functions into context, this is something that we're going to do throughout. It's not going to be something that we slap on at the end of our chapter and try to make real world sense of it. As we go through, we're going to continue to try to do that.
Dennis, thanks so much. And we hope by the end of the webinar tonight, you'll be able to use the TI-84 to develop an enhanced student understanding of a really tough concept, domain and range. Understand the built-in components of the TI Innovator Hub. Investigate strategies for creating classroom discussion of functions. And lastly, expand the idea of functions beyond algebraic representations. So with that, Dennis, let me give you control and feel free to share your screen.
Okay, so you should be seeing my screen, and here is my PowerPoint. Let me open up the chats and the Q&A so that I can see what's being said. And so what I want to start with tonight is just the idea that first, the Innovator Hub. And I don't know how many of you might have had experience with the Innovator Hub. Perhaps you have some in your classroom. Perhaps you've played with it at a conference or workshop, and perhaps you've just heard about it, or maybe it's new to you the first time. But the TI Innovator Hub is in all purposes, it's a microcontroller that's packaged really nicely to work with our TI-84 and our TI Inspire calculators. And what's nice about the what's nice about the Innovator is it allows us to do great things first in a STEM class. And so there's lots of things you can do in terms of STEM projects, in terms of engineering, but what we're going to look at tonight is like trying to put it to use in an actual math classroom in different ways. Now, the Innovator Hub allows us to connect various probes and sensors through various ports that are external to it, but tonight we'll be using the built-in onboard components. There's a red LED and there's a red, green, blue LED, and I'll point those out later, or actually I'm hoping that you will notice them as we explore our functions tonight. There's a built-in speaker so that it can produce sound. Now, for the sake of tonight's webinar, though, I have a homemade external speaker that I've plugged in. I'll show you that. I have this external speaker that I plugged in, and the only reason for that is to make sure that our microphone picks it up and that you can hear it in terms of what we do. And so those three are going to produce output for us tonight. And then there's a light brightness sensor on one end, and that's going to take in some input for us as we search for functions. So I want to start with this question: what is a function? And so what I want you to do is I want you to think about this question and pretty much every question we do tonight in two different ways. First, I want you to think about how you would want your students to answer this question. What is it you would like them to give you? And we all know that in the classroom, that's not always going to happen. So what I also want you to think about is, what are the answers that your students are going to give you? What are the phrases they're going to say? It might just be a one-word description or a couple of words put together. And I think it's important that when we have questions that we're going to talk about, that we frame it from both sides. What do we want and what are we expecting from our students? Because this is a key thing we'll want to do when we are trying to orchestrate productive discussion in our classroom. The first step in orchestrating that discussion is anticipating. So we want to anticipate what the students say, but we also want to have a sense for where we want it to go. Okay, we want to make connections between what they say and what we want them to say. So I'm going to give you just 1 minute. And what I'd like you to do in this next minute is I would like you to spend 30 seconds thinking about how would you want your students to answer it. So spend 30 seconds doing that. And then I want you to spend 30 seconds thinking about what you would get from your students. What is it you know that your students coming in from whatever classroom they may have come into, what would they say in answer to this question, what is the functions? So take 30 seconds for your answer, 30 seconds for your students, and at the end of that time, I'm going to ask you to give me some responses in the chat window. Okay, dead time seems like a whole lot longer when you're online than it is in the class. And we aren't in a situation where we can put students in groups and kind of listen to that discussion. So go ahead. I've already gotten some great responses in the chat window, but if you have an answer that your student would give in the class, what are some words, some phrases that your students might just spit out when you ask them, what is a function? So I see that we've got a relation of dependence between two quantities. A function shows a linear relation between input and output. Those are good words that we're wanting to hear. Many would say that's a line on the graph without thinking. I like this one, shoulder shrug. You know, I don't know, what is a function? A function is a relationship between input and output. A set of inputs and outputs. A function is a relationship between X and Y. So we have this wide variety of answers from students. And what we want to try to be able to do with those is take these different ideas and make connections with them. So what I have here, this is one of the standards of the Common Core. It says, understand that a function from one set, the input, called the domain, to another set, the output, called the range, assigns to each element of the domain exactly one element of the range. Now, we might all have different standards. In Georgia, we have the Georgia Standards of Excellence, or you might have the text. And depending on what your standard is, it might read a little bit differently, but basically it comes down to the idea that the function goes from a domain to a range, and that idea of exactly one element from the domain in the range. So what we're going to do, well, what I want to talk about before we start doing it is this idea of that language. How do we get the students to use the correct language, and how do we move them forward? And so this is a graph that I like to use with my department. My department at my school goes from 6th to 12th grade, and this is how I want them to think about the language that they use and their students are using in the classroom. And you can see that when we start in 6th grade, I'm expecting very little formal or conceptual language to be used by the students. But they're going to, most of their language is going to be procedural. One thing that comes to mind is dividing fractions. You know, these students have their mnemonics of keep it, change it, flip it. It's a very procedural definition. But what I want all my teachers to do is to continue to root those informal procedural words into the formal concept, so that as they proceed, and I get them in calculus, say, at the end of their senior year, I'm using that formal conceptual language and they're comfortable with it. And not only am I using it, but they're using it. And then occasionally there's just times when we have to go procedural. I have to give them a reminder of what we're doing operationally so that they can go forward. So tonight, we're going to be simulating functions on the TI-84 CE. Okay, so you know the TI-84 CE has the y equals window, and where we can store 10 algebraic functions of x. And that's great, but what I want to try to do is separate that idea that function is an equation. That's one of the words I always get. What's a function? Oh, it's an equation with x and y. And I want them to move away from that. And so we're going to be simulating the functions on the TI-84, and we're going to use programs to run them instead. And the reasons we're going to do this, one is I can reinforce language. And you can see right here when I'm about to run program A, it's going to ask for input. So I can reinforce language in different ways with different functions. I kind of make the function like a black box so that students don't think of a function as necessarily a set of arithmetic operations that they perform. You know, it's kind of like, what is sine of x if you were to ask a 9th grader? You know, it's just a black box. And want the student then to try to understand what the function's doing without actually seeing behind the curtain, so to speak. And then the last reason that I'm going to do it is so that we can get output out of the innovator and get input from the innovator. So I'm going to start the first 3 functions here in my TI Smart View. And all the programs that I'll be using tonight are going to be available for download at the end of this session. So if you got questions about how the programs work, or you want to see behind the scenes, I know there's probably some coders here. All that will be available to you at the end of the session. So first thing I'm going to do to simulate a function, I'm going to press the program key, and you can see I just got this alphabet soup of functions that I've already preset up, ready to go. And so I'm going to press enter, and it's going to prompt the calculator to run program A. So I've selected that program. Program A is in that entry window, and I press enter to run the program. And the first thing it does is it says input equals. So if somebody would, please suggest an input that I could give this calculator in the chat window if you have an opportunity. Okay, so I see 5. So I'm going to press 5, and I press enter, and it tells me output equals 10. So what I want the students to do is to take a few values so that when they get their output, they can make a conjecture about what the output would be, and then test that conjecture as they move forward. So I'm going to do a couple more that I've got in the chat window. And notice I didn't go back to the program menu here to run this function again. Once that program's run, if I just keep hitting enter, the students don't have to continue back to the program menu to get it. They just hit enter, and it'll prompt them for the input again. So I press 6, and I get an output of 11. I press enter to run the program again, try 11, and I've got a 16. So hopefully we have a conjecture in our mind now as to what kind of function this is going to be. And so we got a great conjecture there, input plus 5 in our chat window. So what I want to do now is that when I run the program, I want to decide what input I'm going to have and test it based on what I expect the output to be. So I should have an input and an output in mind so that I can test my conjecture. Now we're getting a lot of integer values, And actually, we're just getting a lot of natural numbers. And that's typically what students are going to do. They're going to want to put in these values. But let's try some other values. Let's try 0. And so when I hit 0, I get that the output is 5. So it looks like it's adding. Let's try some negative values. So -5. And I get 0. Or let's even try some approximations to irrational values. I'll run the program one more time, and I'll enter pi. And hopefully our students know pi well enough to know that's 5 more than pi. So what we're getting with this function is the idea that everything's being increased by 5. So as students are going through this, each student gets a card with for each particular function that I might have them do. And I'm walking around the class and I want to hear the conversation as they try to do certain things and fill out certain information on this card. And so in words, I want them to be able to describe the relationship of the output to the input. Students need to be able to verbalize these operations to say that the output is 5 more than the input. They need to be able to write an equation for a of x. Okay, and we have that in the window that a of x is equal to x plus 5. And then they need to be able to understand what is the domain, what are the values that I can put in, and then what are the values that I can get out? What would the range of this function be? And then I like to just kind of extend it to perhaps something that I might not talk about fully, but that it starts to plant seeds in their mind so that when I can come back. So it says, is there a function that takes the output of a of x and returns the input? Is there something that takes me back to that? So as I walk around the class, I'm monitoring what they're saying. I'm looking to select what certain students say so that I can call on them when we discuss, and I'm going to sequence it in the order that I want. Now, you might be hearing these verbs and be familiar with them, and they're in your mind, and we're going to talk about what those verbs are in just one second. But once I've done that, once I've monitored the class, I have selected students that I want to engage in the discussion, sequence them in the order I'm going to do. What I'm going to do then, we're going to connect those ideas. And so some of the things I want to make sure I connect with functions: verbal description and relationship, domain and range. I want to bring it back to that idea of an algebraic equation for a function. It's not always there. This one is huge for me as a calculus teacher, the function in a real world context. Every year on the AP exam, students are asked to explain the meaning of an algebraic expression in the context of a problem. And so if I can start putting real world context to some of these functions, it's helpful for the teachers down the line. And then other concepts that might be connected to the function. So I just hinted at perhaps inverse functions later on. And so we're trying to connect those concepts. And so I just want to put a plug in for this book, which really changed the way I teach math. The 5 Practices for Orchestrating Productive Mathematics Discussion is by Smith and Stein. It's an NCTM publication, and this is actually the first edition. I couldn't find a good high-resolution picture of the second edition, but I highly recommend that if you don't have this book on your bookshelf and you haven't read it, to go ahead and do that. All right, so that's the idea. We're going to look at functions for the rest of the time, and what I want us to do is to have these things in mind as we move forward. In the materials you get at the end, you'll have a sheet of handouts that's all the cards that might go with these particular functions, but we won't look at them each one individually. So before we move into the Innovator, what I'd like to do is to do 2 more functions right here in TI Smart View. So the next one I'm going to do is program, and I'm going to choose function B. Okay, so I only got to go to the program menu the first time to select it, and each time after that, pressing enter will run that again. So I'm going to press enter, and notice right away, no longer am I asking for input, I'm asking for X. And so that's one thing I'd mentioned that I like about simulating these functions, is that I can change the language based on what I want to guide that discussion in the way I want. So X equals. Who would like to suggest a value of X in the chat window, please? All right, so I like it from Janelle. Janelle said 1/2. Okay, So what's nice here is that I can actually type that expression 1/2 right into the window as a fraction. And so I'm going to press enter, and it tells me that y equals 200. Okay, so in your mind, keep an eye, try to start making a conjecture of what we get. We're just going to take 2 or 3 of these, and then we're going to ask for a conjecture what's going on. Saul went with the negative integer, so -2. I'm going to press enter, and I'm going to get -50. Okay. Ken went with my favorite number. Ken, I really like the number E as a calculus teacher, so I'm going to put number E in there. And I don't quite get the sense of what I want from that. And then I see 3/3 y. I could put y in here, and all y is would be a variable that the calculator had stored. And if I don't know what y is beforehand, I'm not going to get much information out of it. I'll try Rebecca's suggestion of 11/22. Ooh, 11/22 is 200. I got that for 1/2. So Robert, why don't I try Robert? I think he's onto something. He says 100. When I put in 100, I get 1. And then, yeah, that 11/22 was the same as I have. So what's going on here? What is the relationship that we're seeing between x and y? Are we seeing a relationship between x and y? Think about that for a second. I got another suggestion, I've got to think for a second. Where do I get this on the 84? I don't teach complex numbers on the 84. Anybody want to tell me which key? I know it's there. No? I'm feeling it. Second decimal point. Ah, there it is. Thank you. Thank you, Janelle. Second decimal point. I press enter. Oh, data type. Okay, that's unexpected. So I'm going to quit this so it doesn't take me in. I don't have this in an I don't have it in a I have it in a real mode. I don't have it in a complex mode. So it's not going to give me the answer there. But I'll run the program one more time. And do we have any suggestions about what's going on here? What the relationship between x and y is? I entered 100 and I got 1. If I enter 1, I get 100. If I enter 2, I get 50. And if I enter 50, I get 2. And so what's great is to hear students' conversation as they battle back and forth as to what this might be. And all the relationship is that y is equal to 100 divided by x. Very good, Daniel. And so whatever I put in for x, I'm going to divide by 100. And so that brings us to a good point. Is there a value that I can't do this for? Is there a value that I can't put in for x? So 0. So what am I going to get when I press 0? Now, I wasn't ready for I, and I probably should not have approached that, but your kids are going to try it, so I wanted to try it. But when I push 0, I get undefined. Now, that's because I've created this function in the program to give me that answer. Now, if I put 100 divided by 0 into the 84, it's going to give me error, divide by 0, and I'm going to have to either quit or go to. So I'll just quit that. And while I'm getting this error, that's not the language that my students are used to in terms of dividing by 0. They're used to this phrase undefined. And so I like the program that it will tell me undefined. And I can communicate to my students then, well, what does it mean that it's undefined? Why did your teachers call it undefined? I don't know. They just said if I divide by 0, the answer is undefined. Now, what does it mean to be undefined? And I love to hand a dictionary to a student and tell them to find the definition for some made up word. And they'll go searching for that definition and they're like, it's not in here. And that whole idea is the same here. They went my program went looking for 0 in the domain, couldn't find 0 in the domain. It's like, wait, there's no definition for 0. There's no output for 0. So it's undefined. Another great thing you might talk about here is the idea of what context this might be. Okay, what use would 100 divided by x, what use might I have for that function? One of the things I could do is restrict the domain. And if I restricted the domain so that it only took certain values, like 25, it could tell me the way to make change in to $1. Ooh, so Daniel wants to look at complex mode. I think we just have just a little bit of time. Let's see, mode. We'll go down to A plus IB, and we'll run program, and I will do second decimal for I. Ooh, my calculator, it might be just the way I programmed it. No, I'm not quite sure why it's doing that, but that's all right. It's always good to kind of play and explore, especially as teachers, before we get into the classroom. Okay, so I'm just going to change the mode back to real, and let's look at one more function. Oh yeah, Daniel understood, like if I do 100, if I had done 100 divided by I when I was in complex mode, whoops, there, then it would have given me that answer. I was interested if it would give it to me here in my program, and I'm a little perplexed as why it didn't, but that's okay. So I'm going to go program, and we're going to do one more function, program C. Okay. Well, we didn't really, wait, before we move on, the domain and the range of program B. Hopefully we understood that, like, sometimes when we talk about domain, the best way to express the domain is by what's not in the domain, right? The domain is all real numbers except for 0. And so for students to understand, all reals but not 0, that, like, I can't name all the numbers in that domain. It's a whole lot easier to name what's not there. Okay, so program C, it says x equals. So who wants to, if somebody would give me a real number to try here, and we'll see what we get. Display the program. Okay, Jonathan, I can show you the program in a minute, but I see 23 from Janelle, so I'm going to put 23 in. And here, once again, I'm making use of the program's ability to give notation in different ways. So instead of y equals, I've got C of 23 equals 1. Okay, I got 22.3, and I press enter, and it tells me that C of 22.3 is undefined. And then I've got -5 in the chat window. C of -5 is 1. And Jose suggests pi. So second pi. And it tells me that C of pi is undefined. So I'm a bit perplexed now. I've got certain numbers that are giving me values and certain numbers that aren't. So do we have a conjecture as to what the domain might be for this particular function? We put in -5 and got a value. We put in 23 and got a value. But if we put in any of those rational or irrational numbers, we didn't. So I'm tempted to think that the domain might be the set of integers. Oh, thank you, Carl. And so I'm going to run the program again. And so now my conjecture is the set of integers. So I'm going to put in some integers. So I'll put in 4. I put in 4, I get 0. Run it again. And you know, at this point, students are probably going to come up with some scheme to try to see a pattern by just going along with what they chose. So I'll go 4, 4 is 0, 5 was 1, 6 is 0, 7 is 1. Ooh, it's asking, is the integer odd, Myra said. Okay, and so if it's an odd integer, we're getting what? Okay, so somebody suggests -3, there's an odd integer, and we get 1. If we put in an even integer, 24, we get 0. And so it could be a piecewise, we could think of it as a piecewise defined function, that if x is odd, the answer is 1. If x is even, the answer is 0. We've got the modular function base 2. And so students who are a little more advanced might have done some modular arithmetic. We could connect it with what is the remainder when I divide this integer by 2. And so what they're seeing now is, okay, this function has a weird domain, and it could come out from a piecewise function if we wanted to write it like that. It could come out with just stating at the beginning that we're only going to use integers. One of the things I like to do is ask, what use would this function be to us as students? And what's nice about this function, I call it a light switch function. Because if I flip the light switch that's off, well, it would only work for the positive numbers. But if I flip the light switch an odd number of times, it's going to be on. But if I flip it an even number of times, it's going to be off. And if you've ever looked at those power switches on the back of your computer, you've seen the 1 and the 0, the on and the off. And so the students can kind of make that connection with what's going on with that function. So we got an idea of how that's working. So what we're going to do now, we're going to switch to my handheld. Okay, let me turn it on. Hopefully you can see that well. And so I've connected my TI-84 plus CE to my TI Innovator Hub, and this green light is on. Okay, this is the green light that tells me that I have a proper connection between my hub and my 84. And so if I don't see that green light, I need to check my connections. That's the first thing we need to do before we start running programs. Okay, and so I put those same programs into this calculator, and we're going to go to D now. Okay, and so when I press enter for D, it asks for input, just like all our other functions did before. Okay, now what I want you to do is you've got to pay attention to the Innovator Hub when I put in a value. So who has a suggestion for the input? All right, so Janelle says 2, so I'm going to put in 2 for input, and I'm going to press enter. So watch the hub. Did you see it? I'm going to move the cursor to where I want you to look. Can you guys see my cursor? I think you can. I want you to look in this area when I do 2 this time. So I press 2, and I press enter. I got a red light. And you know what? Hold on. That did not look right. Let me try 3. Oh, there it goes. You can see better with those 2 numbers. I don't know why it didn't look quite right with 2. Let me do 5. I think it's partly my document camera, because with my eyes, the blink is more apparent than it is with the document camera. But when I put in 5, what I got was 5 blinks. Okay, so I'm going to put in 7, and well, first I got to run the program. I'm going to put in 7. Let's see if we can get 7 blinks out of that LED. 1, 2, and then it's kind of going solid. It's blinking on this end. So you can kind of see the blinks. And so we put in some numbers, and we can see that the number we're putting in is how many times this red light blinks. So what do you think the domain is? If you would, in the chat window, what do you think the domain of this function would be if the output is blink? Okay, yeah, unfortunately, well, somebody earlier wanted to see the program. So let's go to the program, and I'm going to edit program D, and I'm just going to make it blink a little bit longer. Hold on. All right. So hopefully you'll see it a little bit better now. I'm going to put into, let's see. It goes on. It goes off. It goes on. It goes off. Okay. So how many times are we going to be able to blink? And so I got 2 great answers in there that I like. Is it non-negative integers? is it the natural numbers? Okay, what's the difference between those two sets, the non-negative integers and the natural numbers? So I'm going to try 4 while you guys think about the difference between non-negative integers and the natural numbers. So 4, it's on 1, 2, 3, 4. So natural numbers don't have 0. They start at 1. So the question might be, is 0 in this domain? What do you think? Should 0 be in this domain? Is it possible to blink 0 times? So Jose says no. I put 0 in, and I didn't get anything at all. So my calculator didn't say, wait, there's a problem with that, because the way I decided philosophically is that it blinked 0 times. Now, if I decided to go forward and say, hey, can you blink half a time? Well, I can only blink an integer number of times, so I get an undefined number there. Or if I say 2.5 times, I get undefined. Okay, and it's saying done because it's done with the program. That's just a consequence of the fact that I'm running it as a program. But yeah, it's saying it's done. And I can't blink a negative number of times either. So this function has a domain of perhaps the natural numbers if you believe you can't blink 0 times, or it would be the non-negative integers if you believe that it can. Okay, and students like to engage into that philosophical argument. You've got students that might not want to at first venture into a mathematical conversation, but this could engage them if they have the opportunity to decide, can you blink 0 times? Okay, so let's look at the next program. This is program E. And this time I've got a slightly different variable. Instead of input equals or x equals that we've seen, now I'm saying t equals. And so here's another reason I like using the program, because it hints to the student sometimes what it might be asking for. So t equals. And so as math teachers, we might be thinking that t is what? Yeah, we're thinking it might be time. So what might be a good time to enter here? Okay, 0.01. So I'm going to put 0.011, and let's look at that same LED again. And it's going to be quick, I think. Ooh, I think it was so quick that the calculator didn't even do it. So let's try a little bit longer time. Yeah, laughing out loud. So let's try 1, and the light came on and went off. If I try time 2, the light comes on for twice as long. Myra says 15. And so some of these functions, you need to caution them, okay, be careful of big numbers, okay? 15, this light is going to stay on 15 seconds, okay? And once the student realizes it's going to do certain numbers for a certain length of time, they might go, wait, let's do it really long. So it would seem that this is the amount of time that our red LED is staying on. So what might be the domain of our function E of t? What might be the domain of E of t if it's giving the amount of time that it's on? Is it going to be different than what we had for F of t? Okay, so somebody wants to try 3.5 to test their conjecture. So real numbers greater than 0. So I will put in 3.5, and the light comes on for 3.5 seconds. And so as long as that time seems to be positive and not too small that my innovator turns off before I can turn it on, then I can get those lights in. And so it would seem to be real numbers greater than 0. Okay, so let's go to the next function, which will be f. And it wants an input. So Again, you caution your students. I'm going to pick an input here. Ooh, we'll go with 7. Myra chose 7. 7's small enough for me. And you guys hear that? Were you guys able to hear the sound well? We did a sound check earlier. Good. The sound was good. Hopefully it wasn't too loud. So you heard it, 7, and it went on for, I don't know, it went on for a certain amount of time. Let's try a smaller value. Let's try 2. So 2, it went on for a shorter amount of time. Let's try something in between. And while we're at it, let's get out of those integers. Now, if you're not tone deaf like me, hopefully you're recognizing that every time it's the same frequency, but the time we're putting in is a different amount of time each time. And so the sound tone is staying constant, but the input, what it does is it changes how long that sound is on. Okay? And so to move forward in terms of the time that we have, that we hit everything, this is a good opportunity to be philosophical again. Can you turn the sound on for no time at all? You know, kind of get into the argument of if a tree falls in the woods, does it make a sound? So let's go on and do program G. Input equals. Now, I'm going to, for the sake of time, put in some values so you can see how G differs. I'm going to start with 400. And like I said, you want to kind of coax them into certain values. But hopefully with 400, you heard that tone was a little bit different than we had before. If I go 1000, we get a higher tone. And so Jose's asking, could it be the pitch? And so maybe we could go to 2000. And so we might ask our students, what is the frequency? I'm sorry, what is the range for this function? Because it's the frequency that's going to be put out. And I didn't change the program to accept different frequencies, but here we're in a real world context. I have a speaker, it has a certain size, and based on that size, some frequencies can sound good, but if I try to get low and do bass, I don't know if you were able to hear that. You got a little bit of a vibration with that. Or if I got to try to go really high, like it's a tweeter, my speaker doesn't do well with that at all. Okay. Or if I go 20,000, that I see that, Janelle. How old are your ears? If I do 20,000 and I've had a speaker that could produce that, then I wouldn't be able to hear that at all. And so not only does the speaker decide what the range of the domain of this function is, but maybe even the person who is listening. In terms of amplifying them, in terms of modulating the amplitude, that's not something that you could do in the program. So there's two things that I can do is change the time interval and change the frequency. And then based on certain speakers, you could adjust the volume of your speaker if you wanted. So this next function is a little bit different. There's no innovator output, but I'm going to, let me just run that one more time. I meant to run program H. Okay, and this time it prompts us with A. Can somebody tell me what A might be? Give me a value that I might try for A. 700, 10. I'm going to go with 10, 700. That's a nice big number. And I just happen to know where it is. And so I did 10. Wait a second. I gave it 10, and then what did it do? It asked me for B. This is like a multivariable function. Do you guys teach multivariable functions? Do our kids have to deal with multivariable system of equations? Okay, there's a whole lot of different mathematical rules and equations and laws that students learn that have multiple variables in them. And depending on the relationship, one of those variables could be a function of those other variables. So Who wants to, I've got A is 10. Who wants to give me a value of B? 5. So I'm going to put in 5, and I press enter, and I get 11.18033,989. Now, as math teachers, that the fact that I got this approximation of an irrational number, I start thinking what it might be. But students, they're going to have to play with this one for a while. And I really like this one because some students stumble upon what it might be. Some students are completely lost. And Janelle's already thinking, wait, it might be the Pythagorean theorem. What was it, Janelle, that made you think maybe Pythagorean theorem? There was a reason that I decided to use A, B, and C to hint at that relationship that the students are familiar with. So if it's Pythagorean, students might think, well, let's try our old friend 3, 4, and what should I get if this is Pythagorean? I should get 5. What's really nice is occasionally students just start with 1 and 1, and to have that student recognize that that is the square root of 2. You know, it's good for students to play with numbers and see things and start making connections with decimal representations for approximations of irrational numbers. We don't have to know everything, but if we're familiar with things, we start making connections in math a whole lot quicker. So what would the domain for A and B be? If this is the Pythagorean theorem, what would you say should be the domain? So to me, the domain, if it's a triangle, it should be rational numbers, Jose says. So if I put in -5, it says undefined. Because if I'm dealing with a triangle in my mind, I'm getting those positive rational numbers, okay? Triangle won't have 0 for a length. And so I should only be putting in positive numbers here. So the next program, I, is similar. I press enter. Oops, got my desk from shaking. And it asks for X. And I'm just going to give you some values, 3, 4, and it tells me I of the ordered pair 3, 4 is equal to 5. And I start thinking, well, this might be the Pythagorean theorem in a different context. But if I put -3 and 4, I still get 5. And so for the sake of time, we'll just say this is the distance of a point to the origin. How far is X and Y from the origin? And so this function is very similar. X squared plus Y squared will give me I squared, or if you want, the square root of X squared plus Y squared is the output, just like the square root of A squared plus B squared was the output for H. But are they the same functions? They have the same algebraic relationship, but would you say they're the same functions? This is an important question for our kids to consider because they think the function is the equation. But what we're dealing with here is not equations. We're talking about a domain and a range and the rule that relates them. And so they're not the same functions because we're dealing with different domains. So once students get familiar with multivariable functions, we can go back now to the innovator. And so I'm going to run program J. And this time it asks for frequency. I like to be able to clue them in certain situations what I want. So we'll go with 440, which I believe is an A note. And then it asks me for time. And so I press 2. And it plays an it plays an A note for 2 seconds. And so students can play around and they can see, I think it's important sometimes that if we have multivariable, that the domain of one variable could be very different than the domain of the other variable. Time can stretch on and be any value. These frequencies were kind of limited in terms of the sound that we could do. Now, once they've played with that, what I like to do with my class is give each student a note, and we play handbell choir. And so student 1 has to take his quarter note for a B, and they're going to run that program and do a frequency of 493.88. And because it's a quarter note, they're going to run it for a quarter of a second. And so we'll just run that program real quick. 493.88 for 0.25. And so I have each student load up their calculator and are ready to press enter. And then the conductor takes them note by note, and we get a nice little bell choir. And this happens to be, I can't read music, but my son would look at it and he would tell you right away that that's Ode to Joy. But it's a nice thing to engage them with that technology a little bit as an extension. Okay. I'm going to skip K, but if you have an Innovator, I suggest that you play with program K and see what it does. But what I want to do a little bit with the time that we have is I want to talk about this brightness sensor. And so hopefully, let me change screen so you can actually see the brightness sensor. Okay, so we have this brightness sensor at the end of the Innovator, and it takes in numbers based on the brightness that we have. And so I've got a program L, or function L is what I'm calling it. And what it's going to do is it's going to take in values based on the brightness. I'm going to turn this to the side just for a minute so that that brightness sensor doesn't get blocked by my cable. Or I'll just set it up on the calculator like this. So the brightness sensor is right here where my finger's pointing. And when I press enter and run program L, it's collecting brightness data. It depends on what kind of light that's getting. And those numbers are pretty small, but I'm going to take my flashlight, and by putting my flashlight at different distances, I can get an output of different values for the brightness from that function. So do it one more time. And so by changing the light's distance from the sensor, I get different values. And you can see if I get too close, it's 100 and it doesn't get any brighter than 100, but it seems to be between 0 and 100. So this is a nice thing for them to play with and investigate. You know, you could say, okay, let's see, how does that brightness that I'm getting out depend on the distance the light is from that particular brightness sensor. Another thing, though, that this points to is the idea of composition of functions. So we were getting an output based on that numerical value between 0 and 100. And what we could do is we could create this function M. It takes in a brightness, gives us that number, and it takes that number and plugs it back into our function F. And so, Janelle, the programs are there, and you can see how in the program it could collect a specified number of values. It's just a for loop if you're familiar with programming. But any questions you might have in terms of the programming, once you get the files, my email is available in the handout, and I would love to hear from you. But in terms of this composition, we get a brightness of light, which is a numerical value, and we plug it into our function F. And remember, our function F was playing a sound. And so we're taking a composition. We're taking the input of the brightness of the light, and we are changing it through a composition into a sound. And so we'll run that program real quick. Let me see, program, and that's M, which is our composition. They're all very low frequencies because of the range. And so a nice exercise for the student is perhaps instead of just a composition of these two functions is to have like a helper function in the middle, maybe a linear function that would change the values I'm getting in brightness to frequencies that I would want. So I'm going to go to, go go back to my calculator, and I'm going to run this. I'm going to run what's M1. Let me pull up M1. I'll run it one time so you can hear I get different values because I put in a helper function to change the brightness I was getting to a range that was more complete. And it's almost like I've got a really low-tech theremin, or maybe it's a really high-tech theremin. But students can explore and play with the types of functions. So if I'm studying linear functions, I've got 0 to 100 in brightness. What is the output that I want for my linear function in terms of frequency before I play it? And so students can come right into this program and edit it. And you can see right here on the line, this is the linear function I decided to use for F. You might want an exponential function because that's the way the musical scales go. And so you've got lots of different opportunities to play with functions and connect students with the real world input and the real world output. Now, we don't have enough time or space to look at it with the rover, but the same thing could be done with the rover. And in the programs that you're going to get at the end, there are 2 folders and they have different functions you can use with the rover. I like using the rover to explore reference angles. Give it an angle and it turns all the way around, whereas another function just turns the shortest angle to get to that. So helping students understand how reference angles can give that same terminal point but not be the same angle. There's an activity for helping students learn the distance formula by plugging in the sides of a right triangle, or to explore and finding the regular polygons. And so those are available as well. And like I said, on all the handouts, my email's there. I would love to hear from you. Please feel free to reach out and email me if you have questions or suggestions. If you want more information about how to code with TI, I recommend going to this site, 10 Minutes of Code. It's got a great place to start if you're completely unfamiliar, but it has some great extensions using the Innovator if you are familiar with TI Basic. So with that, I hope that this has been beneficial. I hope that you guys have an opportunity to try these and play around and reach out to me and let me know. Mike, you good?
I'm good. If you can hand things back to me, I'll do a
Oh,
really quick
yes. I'm
wrap-up.
sorry.
It's all good.
I
Thanks,
dropped the
Dennis.
ball. Here's the ball.
Thanks so much, Dennis. To receive a certificate of attendance for tonight, go ahead and click the link in the chat window. If you're watching this on demand, go ahead and copy that link into your favorite browser. Unfortunately, we had an issue with the documents link for tonight, so I apologize, but the documents link will be coming. You'll receive an email within a couple days with that documents link that Dennis was referring to, and that follow-up email will contain a link to the documents, the certificate, and the recording as well, so you can follow along at your own pace.
And Mike, I went ahead and put my email address right there in the chat window. If you guys want to go ahead and email me before that comes out, feel free. I appreciate that.
Dennis, thanks so much.
Thank you, Mike.
And if you're in need of any post-webinar follow-up, feel free to give us a call at 1-800-TI-CARES or send us an email, ti-cares@ti.com. We'd love to hear from you. When you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback really guides us as we plan future online events, and we really hope you'll share your thoughts in that post-webinar survey. Huge thanks to Dennis for helping at least me realize what my TI Innovator is capable of and helping me connect that with some concepts that I already teach, and this would definitely be a unique and different way for me to teach functions. So thanks so much for putting all that together. We really appreciate it.
Thank you, Mike. I really enjoyed it.
And thanks to everyone for joining us tonight. We hope to see you back online next week. Have a great night.